Welcome and thank you for joining us today. My name is Paul Donahue and I will be your host. We ask that you please keep your device muted during the session, and if you have questions, please direct them to me via the chat function. We'll do our best to answer questions at the end and to follow up with any unanswered questions via email. As I think you know, these tech talks have been designed to provide straightforward insights into radio frequency components. We'll cover applications, related technology, and the design and engineering enhancements that a custom manufacturer such as Quantic TRM adds to align with each customer's application. To share the details, I'm pleased to introduce Quantic TRM's Chief Technology Officer, Shaun Moore. The author of 2 U.S. patents and a number of white papers and technical articles on passive microwave technologies, Shaun has been with the company since the late 90s, and his passion has only increased over the years, especially when it comes to solving customers' design and engineering challenges. Welcome, Shaun. Can you share an overview of today's session?
So really for today, what we're going to talk about are power combiners. There are 2 main classes of power combiners, and really we're going to go through at some level of detail, the differences between them and why you would pick one over the other. So we're going to start basically by going a very brief review of what power combining is. We're going to then present the concept of what an isolated power combiner is, move into a non-isolated power divider, which again is sort of the other class of power combiners. Then I'm going to go through a little bit of detail, which is specific to the non-isolated power combiners. It really talks about where does that energy go, or the non-combined, non-coherent energy. It does go somewhere. We can't destroy energy. We can't make energy. We can only redirect it, and it has to go somewhere. We're going to talk about where it goes, specifically with the non-isolated case. We'll then do a quick review of what we talked about, and then go over what TRM has as key differentiators for our customers.
Well, thank you, Shaun. That sounds good. And maybe to get started, you could give us that brief review of exactly what a power combiner does.
Absolutely. So a power combiner really just takes the energy from 2 devices and vectorially sums it. The word vector is a big deal here because what happens is energy is summed in such a way is that the vectors add. As you know, vectors only add if their amplitude and phase relationships are the same, or what we call coherent, which means that they're aligned with each other this way here, so that when they add, the vector gets bigger when they add. If they're in opposite directions, they will actually subtract going through there. So we have to really understand what happens with the energy coming out the sum port of the power combiner as to whether it adds, in which case it goes out that sum port of the power divider, or if it subtracts, it has to go someplace. And where does it go? Really talking about what we're talking about here between differences between a isolated power combiner and a non-isolated power combiner. In a nutshell, the sum port is essentially the same. What's different is that differential energy. Where does that energy go? And that's really the big difference of what we're going to talk about here today.
Okay. Well, maybe we could start by talking about isolated combiners and go from there.
Sure. So now the isolated power combiner really is the kind of the prototypical power combiner. What happens here is you have 2 different sources. The energy is summed from all of the inputs, and it directs the energy towards the sum or the combined output port. Any energy that does not vectorially sum very neatly and wants to be subtracted is directed towards a resistive load, and that energy is dissipated as heat. In that case, combining efficiency is really dependent on how well the sources are in phase with each other. If they are in phase, then the combining efficiency will be quite good. If they're out of phase, then the efficiency could be easily as high as 50%, where half the energy that you put in for the various inputs gets dissipated as heat in the isolation circuit. Another thing of very note here, since we're going to be talking about the next class of the non-isolated power combiner, which is something that we don't really talk about when we talk about isolated power combiners typically, is that the amplifiers, regardless of the phase relationship between the various amplifiers that are being combined, each amplifier will see the same VSWR regardless of what its neighbor amplifier is doing. And in that case, the two interaction of those two amplifiers are isolated from each other, which is what we mean by saying that they're isolated power combiners. The amplifiers do not know or care if there's another amplifier in the same system that's either running in phase with it, in which case we're getting efficient combining, or out of phase with it, in which case we're getting a lot of subtracted and wasted energy. And basically, with this sort of device, the better the isolation that you have between the power combiners, the less variation you will see for the output of each amplifier in terms of VSWR. As the isolation degrades, so does the interaction between these amplifiers will begin to increase.
Okay, and what are the differences then with a non-isolated combiner?
Okay, so a non-isolated combiner comes through, and basically what happens is that just like in the isolated combiner, all of this energy that adds vectorially gets summed and gets put out of the common port. That is no different. So that is the same. What's different here now is that anything that is a differential energy, or the energy that subtracts because the vectors are pointing in opposite directions, that energy has to go somewhere. And if it's not going to go out the common port, it has to get reflected back out the ports that it came into, and it ends up being reflected back into the amplifier that the energy came from. So, or essentially back to its source. The definition of VSWR, or voltage standing wave ratio, is the ratio of energy that is sent down the line versus energy, how much of that energy is being reflected back. Is the ratio of those two power levels that determine really what VSWR is. So what happens is with a non-isolated power combiner, and you have power combiners that are not in exact sync with each other, that differential energy will begin to reflect back towards those source amplifiers, and the amplifier will think that it is running into a higher VSWR load. Exactly how high and how much change that you get with that load really depends on the magnitude of the differential energy. An example here is now if the amplifiers are perfectly matched and running in exact sync with each other, there will be absolutely no performance differences either for total combined power going through the power combiner, or the actual effective VSWR that the amplifier will see as energy being reflected back to it. Because if we are in perfect sync, there won't be any energy being reflected back towards the source amplifiers, and therefore you will have a very efficient and very good performing system. In that case, there will be virtually no difference between an isolated case and a non-isolated case.
Okay, could you tell us a little bit more about where this energy goes?
So absolutely. So really, the big thing here is that, and this is sort of a reiteration of what I was just saying here, is that with a matched system, the energy goes right through and then comes out the common port. When you have differential energy where the vectors are being subtracted, would that energy be reflected back towards the source? And that's really the big difference. For both configurations, the insertion loss, the VSWR the amplifier sees, and the VSWR at the combiner point would be the same if we have a good match in both phase and amplitude of the various amplifiers that we're combining. Only when we have that difference in amplitude or phase would we actually see higher VSWRs being reflected back towards the amplifier.
Okay, so when would an isolated versus a non-isolated be the right choice, or vice versa? When would we select one over the other, or when would you make that selection?
Sure. So really, this goes into the case of an isolated power combiner. Really has the advantage of having a stable VSWR for the amplifier, and that is really the one thing about it that is definitely a big advantage. It makes a very stable load for the amplifier to see into. Also, since the amplifier is looking into a well-matched port, or not having that much energy being reflected back into it, there will be less heat generated within the amplifier itself. And really, so instead of having that energy being reflected back into the source generator, again, conservation of energy, that energy has to go somewhere, and it gets poured off into the resistive termination inside the power combiner. In which case, the heat does still happen in the system. It just happens in a separate device from the amplifier. So the amplifier itself can run a little bit cooler here if there is any sort of a mismatch energy coming in there, and that energy can then get poured off into a resistive load and dissipated as heat in another device.
So what are the pros and cons of a non-isolated power combiner?
Okay, so non-isolated power combiners have several advantages. First of all, because we do not have to generate an isolation circuit or a loss mechanism in the resistive load, these circuits are usually far simpler, and therefore they're lower cost circuits. Also, because they are simpler circuits, when you get up to combining multiple amplifiers, you get up to combining 6, 8, 10 amplifiers. The interconnection of those isolation circuits gets quite complicated, and it also adds a great deal of size and room and everything else in the combiner. So they really add a lot of complexity, as well as making the part physically larger. So I think that there's some very good advantages to going with a non-isolated combiner for various configurations. Also, with the non-isolated power combiners, typical radial airline type combiners are very popular. They have very low insertion loss mechanically. They can be packaged in a nice compact package, and there's a lot of good things to be had going for a non-isolated power combiner. Instead, for a lot of applications, it really ends up being the most effective method for building these sorts of combiners. The disadvantages here is that the amplifier can see higher load VSWRs if the amplifiers are mismatched. And that is something that really you have to go ahead and do some individual analysis on to see how much of a variation you're going to see based on how well you're going to be able to match your amplifiers.
Well, can you give us a few hard examples of how matching the amplifiers impacts VSWR?
Absolutely, Paul. And this is really an important piece here to understand really what it is that it means. What I did here was I generated a couple of very simple models of simple two-section power combiners. And this case here that you're looking at here is for the isolated case. And as you see, at 1 gigahertz, which is what I where I built all these models around, I've got basically 25 dB worth of isolation. Nothing special about it really. What I will say though is that as you vary the phase relationship between the amplifiers, this amount of energy that gets reflected back towards the source will vary very, very little. On this graph, I'm not sure if you can really see it or not, there's a very, very faint red line sitting right at 0 dB, right at 0 dB. That is the power that is going forward on this coming out of the amplifier. And the 25 dB is what is being reflected back towards its source. So in this case, if I have two amplifiers that are matched or unmatched, that energy that is being reflected back might vary by maybe a dB or two. But it's really it's very inconsequential as far as to how much different energy is actually being reflected back towards that amplifier, depending on what the phase relationship is between the amplifiers.
Well, in the non-isolated case.
Okay, I'll just go on that, Paul. So the non-isolated case is the next slide. And again, for the slide that is on the left, you'll see a typical non-isolated two-section power combiner, very similar to the last one. In this case over here, 1 gigahertz, I ended up with 28 dB as opposed to 25 dB on the previous example. And with 28 dB return loss, that's a 1.08 to 1 VSWR, very good return loss. And as you see with the words I put right under that graph, is if I have a 100-watt amplifier running into that sort of a load, I'm reflecting back 0.16 watts being reflected back to the amp. These are two 100 watt sources that are driving into a two-way combiner. Again, very good performance. This performance is right on par with what I would expect with an isolated power combiner. Really not that much different. If I was to now go to the case on the right, where I have the exact same power combiner, the only difference here is now, instead of having the two sources in phase with each other, there's a 15-degree phase error that I introduced here on the computer. And basically, with a 15-degree phase error, the energy that gets reflected back from the source goes from 28 dB down to 18 dB down. Well, what does that mean? That means that the VSWR that the amplifier source is going to see is going to go from a 1.08 and go up to a 1.29 to 1. Now, 1.29 to 1 is still a pretty good load, and that's certainly, most systems can certainly tolerate that quite easily. You're using the same 100-watt amplifier example. A 1.29 to 1 will reflect back about 1.5 watts of that 100 watts back into the amplifier. So virtually, you're still going to get what most people would consider very typical sort of performance with a non-isolated case, even with a 15-degree phase error. 15-degree phase error tends to be sort of a number that we use in the industry as far as to what we could accept. It's a very safe, very predictable number for what sort of reflection that we certainly can accept for these sorts of devices. Move on to the next slide, Paul. I could show you one here that has a very significant phase error. This one over here has a 45-degree phase error between two inputs. With this 45-degree phase error, now I'm beginning to reflect back basically 9.5 dB down is where the reflection is, which is, if I go back to my 100-watt example again, I'm now reflecting 11.2 watts is being reflected back into the amplifier. This represents a 2-to-1 VSWR. For many amplifiers, this is right about the level that they will trip at, as far as to make sure that they don't overheat. So as you can see in my simple case here of two amplifiers being combined in a non-isolated power combiner, you can actually have phase errors up to something pretty close to 45 degrees, and still have the amplifiers continue to run in a very similar way that they would if they were a coherent combiner. And I said, and that threshold really of how much of a phase error that you can tolerate is really dependent on the amplifier that you're using. What I will say also is, with the examples that I've given here, I'm talking about two amplifiers in a non-isolated case. These numbers do change a little bit as you add ports on there, as far as to how quickly they change. All that really needs to be analyzed on a case-by-case basis. And lastly, Paul, if you can flip over to the next slide. In this case over here happens, quite frankly, with both amplifiers. Excuse me, with both combiners. If you have a 180-degree phase shift, no energy is delivered to the load. And for a 180-degree phase shift, either if it's an isolated combiner, all of the energy is going into the isolation circuit, or if it's a non-isolated combiner, all of the energy is being reflected back to the amplifier, in which case it'll think it has an infinite load, or essentially it will function the same as if there was an open circuit on the output of the amplifier. Again, neither one of these are desirable conditions, which is why we have to watch out really what the phase relationship is between the outputs of amplifiers whenever we're combining them, whether it is for an isolated case or the non-isolated case here.
Well, it's a lot of good information. Maybe you'd like to summarize.
Sure. So basically, the examples I just showed are simple two-way, two-section, non-isolated configurations. The performance of the combiner really depends on the exact nature of the circuit. There are several ways you can build these sorts of combiners, and that the interaction between the source VSWR, the source phase differential between the amplifiers, and the way the combiner interacts with them is all very much dependent on the exact topology, type of amplifiers you're using, and basically all of the above. So you have to be really analyze this on a case-by-case basis. It's really something they have to be careful of. But with the isolated case, you certainly can be much more lax in your analysis, because all the differential energy is going to be absorbed by the isolation circuit within the combiner itself. And from an amplifier standpoint, that's the safe thing to do. What this basic quick analysis says is that phase variations of 15 degrees across amplifiers are typically pretty safe as far as how much excess energy gets reflected back, and the overall combining efficiency is quite good with about a 15-degree phase error. And basically, the more amplifiers you add to this, the more analysis you have to do, because the more possibilities of interaction just continue to increase. So you have to be careful with that. And you have to look at that ahead of time. So basically, what we're looking at here now is for combining matched amplifiers. There's really no significant difference between an isolated and non-isolated power combiners from a performance standpoint. They work equally well from an efficiency standpoint, and as long as you're matched pretty well, the reflected energy back to the amplifier is very well managed in both in isolated and non-isolated cases. Really, you start seeing big differences once you start going into cases where you have a large phase variation between amplifiers. I've been talking a lot about phase variation between amplifiers here today. Amplitude variation has a much less effect. Phase really is the one parameter that really makes the most difference. You can add vectors if they're in phase with each other, and the efficiency is pretty good if the amplitudes are a little bit different. The other thing I want to bring up here is that the non-isolated power combiners do add quite a few different additional topologies as far as how we can build them, which opens up a lot of packaging options that are not there with the isolated cases, and also that the non-isolated power combiners, because of the reduced circuitry that's involved and reduced complexity, can always be built at a lower cost than a isolated power combiner. And really, when you're looking at sort of combiner technologies, it's important to sit down and do a pretty good analysis as to the different topologies that are available to you. It may surprise you that a non-isolated power combiner may very well fit the bill for you and save some cost and size and weight for your program.
Okay, well, good information as usual, Shaun, and I think we have time for a question. And one that came in, I think we can maybe say, because I'd like to have maybe just talk about the specific things that TRM does differently with respect to designing or manufacturing these types of power combiners.
Sure. So what we do when we work with these is TRM likes to work with our customers, right? So when you're building power combining, it is very much a shared endeavor. You have to understand what the amplifier is doing. We have to work with our customer to make sure that we understand what the loads are, where the energy is going, the sort of phase relationship between the inputs that were coming in. All of these things are important when you're talking about building power combiners, whether they're isolated or non-isolated. I've been speaking today about the isolated case as far as being able to absorb the energy. Well, in those cases, we still need to understand the phase relationship between them. The amplifier may not care really how much of a differential there is between them, but the power handling of the load that we put in these devices does care. And therefore, we have to make sure we understand that whether it is for an isolated case or a non-isolated case. The only thing I think that TRM likes to do with these sorts of things is, of course, we always offer a very robust mechanical packaging, and we go ahead and we work with the customer to make sure that they have the objective evidence that they need. TRM is a solution provider, and that's really what we like to do with this, whether it's for a power combiner or not.
Okay, and we do have one question, as I had sort of alluded to here, and it's Along the lines, you had mentioned that the non-isolated cases can be built for less, but typically what do we save by going from an isolated to a non-isolated case?
Yeah, so like I said, from a performance standpoint, as long as you're talking about reasonably matched amplifiers, really, from a performance standpoint, they're going to work very, very similar. What we are going to say is what we're going to save when we move into the non-isolated case. Basically, is size and weight. These non-isolated combiners can be made significantly smaller because you don't have the additional isolation circuits to include within the package. When you're talking about building a isolated divider of more than 2 or 3 or 4 sorts of paths, the geometry to maintain the symmetry among the isolation circuits can become quite cumbersome. Also, for a isolated case that has many stages, you have to cascade the stages in order to be able to build up to the number of ports that you need. Whereas in a non-isolated case, you can go in there and do it with a single transformer in a radial configuration, for example, and reduce the total length of the part, therefore reducing your total insertion loss. And virtually, if you have matched amplifiers, end up with essentially the exact same performance with from an insertion loss standpoint, end up with lower insertion loss, end up with a smaller part with less loss. So there's a lot of advantages to going with a non-isolated case, not to mention cost. Really, I mean, I think cost is another thing to keep in mind also. Since there are fewer components and the parts can be made smaller, very often or most of the time, non-isolated combiners do cost less than isolated combiners.
Well, thank you, Shaun. And I think a lot of what you have shared with us today supports the summary that's now being shown on the screen with respect to TRM's perspective on partnering with customers. And if you are a customer who joined us today and you have more questions, we hope that you will feel free to call the engineering hotline. The number is displayed on the screen, 888-677-6877. We'd love to hear from you. And of course, there's no cost associated with those calls. If you're one of our field sales representatives, then you know that your calls are always welcome too. And you can also submit questions directly through the sales rep portal. And in case it's helpful, the next Tech Talk will be on Tuesday, October 26th at 11 a.m. Eastern Time. And the topic will be determined in the next week or so. Thank you all so much. And thank you, Shaun.
Thank you, Paul.